Hi, I'm Cris, and this is the first week of Introduction to Calculus video. There's about 52 slides here, so you should go someplace where it's quiet and probably get a bottle of water or something. You can count the slides on the bottom if you want. See right here, you can see we're on the first of 52 slides. If there's anybody else in your family who wants to learn calculus or wants to see if you're getting your money's worth from the online summer course, that's to be encouraged. Another thing I want to mention is that you should probably take notes in some form, whether that's on paper or on an iPad. It's not obvious why you would want to do that, but you should write down the questions you have so you can ask them in class, and that will help everybody. Or you can get discussion points by asking questions about the slides in class. But more importantly, if you write down the things that seem interesting to you, seem important to you, then you can start telling yourself the story of calculus, and that way you'll be able to use it in new situations. When I was a student, I thought it was strange to take notes when I had the video right in front of me, but that was pretty faulty logic on my part, because all the material is in the library, all the material is in the book, all the material is in the slides. That's not really where you want it. You want it in your own notebook in a way you can do something with it and that it makes sense to you. Here's an outline of what we're going to talk about today. There's going to be 4 parts. First of all, we're going to talk about rates of change and tangent lines. Tangent lines give us a numerical interpretation of rates of change. And then we're going to take a break and we're going to just talk in general about why we study rates of change. And part 3 is the longest part. We're going to take some derivatives and we're going to go through the standard so-called elementary functions and talk about their rates of change. And finally, in the last part, we'll go back and give some overall perspective and run through some examples like you'll see on your homework. Okay, so in this first part we're going to discuss the following ideas. First of all, we're going to discuss that the average rate of change is the slope of a secant line, and the instantaneous rate of change corresponds to the slope of a tangent line. I put the instantaneous in parentheses right here because people usually don't say instantaneous rate of change. If they mean an instantaneous rate of change, they'll just say rate of change. Whereas when you mean average rate of change, you better say average. And the third point is that the tangent line is a good approximation to the curve. I think you can see that last point right here. If you're very close to this point on the curve, there's not much difference between being on the tangent line and being on the curve. These lines in red are called secant lines. A secant line is a line between 2 points on a curve. And the idea is as we move the 2 points on the curve closer and closer together, the blue tangent line is attained as the limit of red secant lines. So let's first talk about average rates of change. The average rate of change, delta y over delta x, of y with respect to x over a given interval from x1 to x2, is the slope of the secant line between those 2 points. So when we say delta y, we really read that the change in y is a capital Greek delta, the change in x. If you start at x sub 1, comma, f of x sub 1, right, this is the curve y equals f of x, and you move to the point x sub 2, comma, f of x sub 2, then the average rate of change is an interesting concept. Y starts at this first point where y is f of x sub 1, and we go along the curve till we get to the second point where y is f of x sub 2. And so there's a certain change in y. Delta y is f of x sub 2 minus f of x sub 1. And the average rate of change says, well, you would have gotten the same change in y if y had changed at a constant rate equal to the average rate of change. So this delta y over delta x, the average rate of change, says if y had changed at a constant rate, it would have made the same change in y over this interval. And you can see just by looking at this triangle right here that the average rate of change, delta y over delta x, is exactly the slope of the secant line, the rise, delta y, over the run, delta x. Now let's look at tangent lines. Remember, the tangent line is supposed to be a limit of secant lines. So each slope of a secant line gives us an average rate of change. And as the time interval gets smaller and smaller, the slope of the secant lines approach the slope of the tangent lines. And that's what we consider to be the instantaneous rate of change. We have the change in y over the change in x. This is the average rate of change over the interval from x1 to x2. We take the limit as the 2 points come together. We let x1 approach x2. And that's what we call the rate of change, or the instantaneous rate of change. And our notation for that is dy over dx. The Greek delta has sort of changed to the English d in the limit. If we want to indicate that x is equal to x1, we just draw a bar after the dy over dx and say x equals x1. So we're going to be doing limits like this a lot. It not only gives us the slope of the tangent line, but it gives us an instantaneous rate of change as well. Let's do a basic example. We'll call this a Galileo example because you can think of a ball being thrown into the air. Let y equal f of t equal 4 plus 6t minus t squared be the height in meters of a ball at time t measured in seconds. Okay, so y gives us the height of a ball. And you can just think of this ball as being thrown straight up and straight down. Delta y over delta t is the change in height over the change in time, and so that's the average velocity, well, the average vertical velocity. And we can compute this average velocity over different intervals. Let's look at the average velocity between 1 and 2 seconds. We compute f of 2 minus f of 1 as the change in y, and 2 minus 1 as the change in t. F of 2, well, we put 2 into this, we get 4 plus 12 minus 4, we get 12. We put 1 into this equation, f of 1 is 4 plus 6 minus 1 is 9. And we get an average velocity of 3 meters per second. Fine. But now let's shrink the time interval. Let's just go between 1 second and 1 1/10 seconds, so a very short time interval. We can do the same computation. We evaluate f at 1.1. We get 9.39. Maybe you'd have to believe me. Maybe we can put it in there. I guess we can put it in there. 4 plus 6.6 minus 1.21 equals 9.39, right? And that's an average velocity of 3.9 meters per second. What if we make the time interval even smaller? We look at an average velocity where delta t is only 1/100th of a second. We do this computation again, we get 3.99 meters per second. And so we would guess that in some kind of limit, as the secant line becomes a tangent line, as the average rate of change becomes the instantaneous rate of change, we would guess that 4 meters per second is the true velocity at that moment. Now, this is an idea. The average velocity is something you see in daily life. If you go 100 miles in 2 hours, you say you've gone 50 miles per hour as your average velocity. You not mean you were going 50 miles an hour all the time. You might have stopped. But that's the constant velocity that would have given you the same change in distance. And as we let that time interval go to 0, our average velocity gets very close to 4. And so we say to ourselves, 4 is the velocity at that moment when t is really 1. Now I want to stress that the instantaneous rate of change is an idea. And really calculus is a consistent logical system developed by mathematicians that captures this idea of an instantaneous rate of change. You may be like me when I was younger and find philosophical questions very interesting. You know, are space and time continuous? Are space and time discrete? Right? Is reality like a flip book that goes from page to page? Or can you chop space and time into arbitrarily small pieces? These are kind of interesting questions, but they're not really the pertinent questions. The pertinent question is whether this idea of an instantaneous rate of change is useful. And it is useful in physics, chemistry, biology, medicine, even in business, all kinds of science. This idea of a rate of change is useful. And if you're going to read about these disciplines and study them, calculus is a kind of language that you need to be able to understand and read and write. So let's put the idea of a slope and the idea of a rate of change together here, pictorially in a graph. Here the ball is going up and coming down. Here's t equals 0, t equals 1, t equals 2. The ball gets to its height when t equals 3. That's when its velocity is 0, and then it starts to come back down. Now its velocity is negative as it's coming back down. This looks like some kind of parabolic trajectory that the ball is traveling on over here, but it's not. The ball just goes up and down. We've graphed the height y versus the time, and that's what spread out this line into a parabola. Let's see, so we had an average velocity of 3 meters per second in between time 1 and time 2. You can see that y has changed from 9 to 12, so we have a delta y of 3. And t has changed from 1 to 2, so we have a delta t of 1. So the slope of this secant line is the average velocity. So delta y over delta t is 3 meters per second is the average velocity. But as we let this point come closer and closer to the point 1, 9, the slope of the secant line becomes the slope of the tangent line. And the average velocity becomes the instantaneous velocity of 4 meters per second. So average velocities correspond to slopes of secant lines. Instantaneous velocities correspond to slopes of tangent lines. Okay, so let's try to do this without guessing, right? How do we really know that the velocity of the height at time t equals 1 is 4 meters per second? It certainly looks like it is, but can we do this mathematically? Okay. So let's just go ahead and compute the average velocity over a time interval that's arbitrary. It starts at 1 and it goes to 1 plus h. If we want between 1 and 2, we let h be 1. If we want between 1 and 1.1, we let h be 0.1. So delta y over delta t is f of 1 plus h minus f of 1. That's the change in y. And delta t is 1 plus h minus 1, which is just h. So delta t is just h here. We get 4 plus 6 times 1 plus h minus 1 plus h squared. Here we're just plugging in 1 plus h for t. And we do the algebra in the numerator. We get 4 plus 6 plus 6h minus, well, what's the square of this? Minus 1 minus 2h minus h squared. And we still have our minus 9 here. 4 plus 6 minus 1 minus 9 is 0. There's no constant term. 6 minus 2h is 4h, and we have our minus h squared here. And we're always happy at this point in the computation because everything that does not have an h in it cancels. And so we get to cancel an h from both terms, and we end up with delta y over delta t is just 4 minus h. Is that consistent with what we had before? When h was 1, when we went between 1 and 2, 4 minus 1 is 3. And yes, the average velocity was 3 meters per second. What about when h is 1/100th of a second? Then the average velocity here is 4 minus 1/100th of a second, or 3.99 meters per second, which is exactly what we got. So since we were able to compute every single average velocity, it's not surprising that we can compute the velocity. So the rate of change by definition, right? I put this in red right here because it's really the definition of dy over dt. Is you take the limit as h goes to 0, you take the limit as delta t goes to 0, of the average velocity, delta y over delta t. The average velocity is 4 minus h. So as h gets closer to 0, what does 4 minus h get closer to? Well, 4 minus h gets closer to 4, and so the limit equals 4. And so the velocity at t equals 1 really is 4 meters per second. Okay, so this is a proof that we don't really have to guess. And if you understand this derivation right here, this comes very close to the point of calculus. The point of calculus here, for differential calculus anyway, is that you can compute rates of change by taking limits of average rates of change. Let's do a slightly less physical example. Let's do a business example. Suppose you are an experienced owner of a corner store. Okay, so you run a corner store. You've been doing it for a long time. You know what's going on. Each week, you put 10 boxes of candy on the shelf at $12 a piece, and you sell them all. They're gone. Next week, you put 10 more boxes of candy. But if you have more than 10 boxes of candy, your experience shows you that you need to lower the price by 5 cents for every box past 10 if you want to sell them all. And you do want to sell them all. You want them all off your shelf. So 11 boxes of candy, we have to lower the price by 5 cents. It won't be $12, it'll be $11.95. 14 boxes need to be priced. Well, we need to knock off 20 cents. We need to price them all at $11.80 if we want to sell them all. Okay. But things get worse, right? Sometimes a truck just comes by and just leaves you too many boxes of candy, and you hardly know the reason. Maybe you made a sandwich for the guy one time and he liked it and he likes you and he wants to drive the truck back empty. Who knows? Sometimes you have too many boxes of candy. And in this case, for every box past 10, you need to lower the price by 20 cents on every box if you want to sell them all. So if you've got 40 boxes of candy, you've got to take 20 cents off 30 times. There's 30 boxes past 10, and this brings your price down to $6 each. Okay, so this is just something you know from business experience. How we formulate this mathematically: so let X be the number of candy boxes at the beginning of the week. It's how many candy boxes you're going to start with. And P is the price per box that you need to have if you have any hope of selling all X boxes by the end of the week. And so what we've learned from what's said on the previous slide is that when X is between 11 and 20, when you have between 11 and 20 boxes of candy, the change in price over the change in the number of boxes is minus $0.05 per box. Notice that you can always match up the units here. The unit of price is dollars, the unit of X is box, and so the units of the average change in price with respect to units is dollars per box. And then once you get past 25 boxes, the rate of change of the price with respect to the number of boxes is even lower. It's minus 20 cents per box. Okay, in this case, well, it's not a physics problem. There's no time involved. The independent variable here is boxes of candy, number of boxes of candy. And the change in P over the change in X is the average rate of change of price with respect to the number of boxes. And it's minus 5 cents in one range, 5 cents per box in one range, and it's minus 20 cents per box in another range. Do you always have to say this long phrase, the average rate of change of price with respect to the number of boxes X? Or is there an English word that captures this idea? That's not a strictly mathematical question. Sometimes there'll be an English word, sometimes there won't be. For the rate of change of position over time, there was an English word, velocity. Delta position over delta time is the average velocity. What about delta P over delta X? Is there an English word for that? Do the economists call that something? Or do we just always have to say the average rate of change of price with respect to X? I think the answer's on the next slide. It's in red right here. Delta P over delta X is the average marginal price, and dP over dx is called the marginal price. So we don't really have a curve in this example. We just have a bunch of data points. Number of boxes X, price P. At first the price just stays at $12, and then between 10 and 20 it goes down 5 cents a box. We weren't really told what happened between 20 and 25, so we just put a question mark there. And then we're going down by 20 cents a box after 25. So in this range, the marginal price is minus 5 cents a box. In this range, the marginal price is 20 cents a box. Now I think you'll agree that selling 10 1/3 boxes of candy is not really realistic, but we don't really care. The rate of change of price with respect to boxes, it's an idea. And what we do is we just draw a curve through all these points, and we consider the rate of change of this curve. In this way, calculus can be applied to things like business, which you might at first think would be kind of a stretch to apply calculus to. Alright, so this is Charlie Brown right here. If you're like my kids and you listen to these videos at 1.5 times speed or 2 times speed, so the speaker's voice turns into a high whine, you might need to see Charlie Brown at this flash of yellow in order to know that, oh, we're in part 2. Okay, so we're going to take a little breather right now, do a little motivation, and explain why we study rates of change. The reason is basically because laws of nature and other patterns as well are often much simpler when you state them in terms of rates of change. So let's look at the Galileo example here, where the ball was being thrown up and came down. The time marches very uniformly, 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds. But the height is not a simple thing. At 0 seconds, the height is 4 meters, at 1 second it's 10, it gets to its top at 13 meters, and it starts to come down. Now the rate of change of the height, the velocity, v is dy over dt, it's a simpler thing. Your velocity just keeps going down. It's 6 meters per second up when you start, and then 1 second later it's 4 meters per second up. 1 second later it's 2 meters per second up, and at the very top the velocity is 0, and then the velocity starts to be negative as the ball starts to fall down. We're measuring up as positive. Now if you take the rate of change of velocity, you get the acceleration, and that's even simpler. That's always minus 2. So the downward acceleration of a ball in motion is constant. This is really Galileo's main insight here. It's not the height that follows a simple law, it's the rate of change of the rate of change of the height that obeys some simple rule, not the height. So simple physics problems, the rule isn't stated for the height y, it's stated for the acceleration, which is the rate of change of velocity, which is the rate of change of y. Let's do another example. Okay, let's look at this nautilus shell right here. How does a nautilus shell grow? When a chambered nautilus makes a new chamber right here, the size of the new chamber is directly proportional to how big the shell is already. So each chamber is slightly bigger than the last, the size of the new chamber being directly proportional to how big the chamber is already. So if we call the current size of the shell y, then the rate of change of that shell is dy over dt, the rate of change of y with respect to t. And if we look at this and as it seems, we say this is proportional. The rate of change, dy over dt, is proportional to y, so it's equal to a constant times y for some constant k. And there's a lot of things in nature like this, where the rate of change is proportional to the current size. So this makes sense, that the rate of change should be some constant times y. And it's somehow more understandable than the solution to this problem. What function has a derivative that's equal to k times itself? Well, we'll learn in this class, you may know already, it's an exponential. Y of t is y of 0 times e to the kt. But an exponential function is a fairly complicated thing. You don't look at this nautilus shell and write down an exponential function. You look at this nautilus shell and you write down this equation on the rate right here. The rate of change is directly proportional to the size. Okay. So rates of change often are what you need to look at to clearly see what's going on. Less profound, but no less useful perhaps, rules of thumb are often just simpler in terms of rates of change. The owner of the store doesn't memorize the prices, The owner of the store just knows to knock 5 cents off for every box past 10, and past 25 boxes you got to knock 20 cents off for every box. Okay, so it's the marginal price that really captures the understanding. So this is one reason why we study rates of change. They just make things simpler and more understandable. In part 3, we're going to have to go over a lot of definitions, and your head is going to have to remember a lot of definitions. So we want your heart to help your head here. Your brain has self-defense mechanisms, and if you really don't believe something is important in your heart, it is very difficult to remember definitions and things like that. Now, you can't really tell your heart what to believe, but you can try to help your heart by going back over the motivation we've just talked about the chambered nautilus and the Galileo experiment. And it will be easier for you if you really do think that these things are important. Okay, so this is part 3, derivatives. Charlie Brown's throwing a ball here, maybe that's velocity. So let's start with some definitions. The average rate of change has to do with a function f of x over an interval from x1 to x2. So we look at the change in y divided by the change in x. That's the average rate of change by definition. And that's f of x2 minus f of x1 over x2 minus x1. If we look at this diagram right here, we can interpret delta x and delta y in terms of the graph. So here's y equals f of x. Here's our 2 points when x is x1 and y1 is f of x sub 1. And here's our second point when x is x2 and y is f of x2. The change in the y coordinate here, delta y, is given by the difference of y coordinates, f of x sub 2 minus f of x sub 1. And the change in x coordinates here is given by x sub 2 minus x sub 1. So the ratio is simply delta y over delta x, or the rise over the run. So the average rate of change is the slope of the secant line. And this is the identification we want to make here, that the average rate of change is equal to the slope of the secant line. Now we're going to talk about the derivative, which is a name for a rate of change. Derivative and rate of change is the same thing. So given a function f of x, we can always associate a curve y equals f of x. And then the rate of change of y with respect to x at a certain point x1, which we call the derivative of f, is given by a limit of average rates of change. The average rates of change are delta y over delta x, and we take a limit as the time interval, or as the x interval goes to 0. So as x sub 2 approaches x sub 1. We call this dy over dx, and this is the rate of change. Now we can also write this f prime of x1 is the limit as h goes to 0 of f of x sub 1 plus h minus f of x sub 1, all divided by h. This change of notation here is simply letting x2 be x sub 1 plus h, and then the difference in the x intervals is just h. When we think of the derivative as a rate of change, we usually write it this way: dy over dx, the rate of change of y with respect to x. When we think of the derivative as being a new function, we write f prime of x sub 1. I think the name just comes from the fact that f prime is a function that's derived from f. The rate of change is the slope of the tangent line. So if we take the average rates of change, they're the slope of each one of these secant lines. In the limit, the tangent line is the limit of the secant lines, and the slope of the tangent line, which is dy over dx, is the limit of the slopes of the secant lines. So the derivative here, f prime of x1, gives us the slope of the tangent line at the point x1, comma f of x1. So we figured out a way to find the slope of the tangent line, which is all you really need to do to write down the equation of the tangent line. Now, derivatives here are defined in terms of limits, we've been working with limits in kind of an intuitive way, and we'll continue to do that. What does this phrase mean, though? The limit as x goes to 0 of f of x equals L. It means that L is the unique number that f of x gets closer to as x gets closer to x naught. In other words, if there's some number L such that the function f of x is getting closer to L as x is getting closer to x naught, then the limit equals that number L. The limit equals what the function f is getting closer to. Let's look at some different examples here. Here we have a curve, y equals x to the m. If m is greater than 1 anyway, it looks like this. We go to a point x equals x naught. We look up at the point on the curve, x naught, comma x naught to the m. As x gets closer to x naught, the y values on this curve are getting closer to x naught to the m. Therefore, the limit equals x naught to the m. This is a pretty straightforward example because the point is actually on the curve where the y value is x naught to the m. But as we go over to the second example here, where y is sine x divided by x, we see that we cannot plug x equals 0 into this function. So there's a point missing from this graph. But we can still ask, as x gets closer to 0, what does the y value get closer to? And the y value gets closer to the y value of this missing point right here, which is 1. So because sine x over x gets closer to 1, as x gets closer to 0, the limit equals 1. The limit equals what the function is getting closer to. Notice when we take a limit, it is always implicit, if x is going to 0, that x is never equal to 0. X gets closer to 0, and this function gets closer to some limit, which is in this case 1. We look over in this third example. This is an example where the limit does not exist. We look at the graph y is equal to minus the absolute value of x divided by x. If you take a negative number like minus 3, you have minus 3 over 3. You have minus 1. So we always have minus 1 on the left here. If you look at a positive number like 3, you have minus 3 over 3, which is minus 1. We always have a minus number, a minus 1 here on the right. So as x gets closer to 0, right? As x gets closer to 0, sometimes the y value is 1, sometimes the y value is minus 1. Now the limit L has to be unique, so there is no single number here that the function is getting closer to. Therefore this limit does not exist. And we just write D and E for does not exist. There is a more precise definition of the limit, which we can use to do proofs, and we'll mention that next week. Now here are the limit laws that we want to be familiar with when we take limits. So we're in the situation where the limit of f of x exists as x gets closer to a, and the limit of g of x exists as x gets closer to a. And we want to conclude from this that various combinations of these functions have limits that also exist. So for example, rule 1. The limit of f of x plus g of x is the limit of f of x plus the limit of g of x. Or rule 4. The limit of the product of f of x and g of x is the limit of f of x times the limit of g of x. It's often easier just to refer to these in words. You can remember the numbers if you like, but it's easier just to say that a limit of a sum is equal to the sum of the limits. Or for number 4, a limit of a product is equal to the product of the limits. And you can refer to these rules in that way if you like. Or sometimes people just call them the sum rule for limits, the difference rule for limits, the constant rule for limits, the product rule for limits, and the quotient rule for limits. Notice this if after the quotient rule for limits. This limit on the bottom has to be non-zero, and you need to check that when you apply rule 5 to the limit of a quotient. Let's see some limits that we're going to need to know in this class. We've already seen the limit of sine theta over theta is equal to 1. You should be able to check things like that on your calculator. You can't prove them on your calculator, but if you're way off, you can catch a bad mistake. If we put theta is 100th, we get sine of 100th over 100th, and remember to use radians. You have to use radians. This is a number very close to 1. If we let theta be 0.0001, we get a number very close to 1. So this makes us believe this limit is right. It has to be proved in a different way. The second bullet gives us a limit as n goes to infinity. And it's a nice limit because it gives us the exponential function e to the x. So you have 1 plus x over n, quantity, all raised to the n. That's kind of a subtle limit because 1 plus x over n is a number that's slightly bigger than 1, if x is positive, say. As n goes to infinity, x over n goes to 0, so what's inside here goes to 1. So you might think 1 to a large exponent is just 1. But that's not right. This number is a little bit bigger than 1 when x is positive. And if you raise it to a very large exponent, the limit is actually greater than 1. It's e to the x. If you let x be equal to 1 here, you get an expression for the number e. E is the limit as n goes to infinity, just meaning what? That n becomes larger and larger. 100, 1,000, 1,000,000, 1,000,000,000. 1 plus 1 over n to the n. You can try that on your calculator if you want. For example, if you put in n is equal to 10,000, you get 1.0001 to the 10,000 is equal to this number, which is getting closer to e. Of course, it'll never actually equal e, but the limit is e. And the last one, we have a limit for the logarithm of a, the natural logarithm of a. All these are subtle limits because as h goes to 0, the bottom goes to 0. And the top, well, a to the 0 would be 1. So the top is also going to 0. So both of these numbers are racing to 0. But in the limit, they have a certain ratio. They both go to 0, but their ratio approaches a non-zero limit. And that's the natural log of a. And I tested it out for a few values here on the natural log of 2. Okay, so let's get back to derivatives. We're going to work out average rates of change. We're going to work out slopes of secant lines. And then we're going to take the limit of those slopes of secant lines to get the slope of the tangent line. And that's how we'll be computing derivatives. We'll be computing derivatives and we'll get the slope of the tangent line. So the equation of the tangent line to the curve y equals f of x at the point x equals x naught is just given by the point slope formula. We have a point on the curve, x naught comma y naught. If we know the slope of the tangent line, m, then we can just use the point slope formula right here. Y minus y naught is equal to m times x minus x naught in order to get the equation of the tangent line. The slope of the tangent line is f prime of x naught, and y naught is f of x naught. So this is the equation of the tangent line. And that's a very common problem in a calculus class, to be asked to find the equation of a tangent line for a certain curve at a certain point. Now the tangent line approximates the curve, right? If you look at this curve y equals f of x here, and you look at this tangent line, you can see that the tangent line is a good approximation as long as x is near x naught. So if we look at the y-coordinate of the curve, which is f of x, that's going to be approximately equal to the y-coordinate of the tangent line. So we just add f of x naught onto both sides of this equation, and we get the y-coordinate of the tangent line. So this is a very important fundamental approximation for us, that f of x is approximately equal to f of x naught plus f prime of x naught times x minus x naught for x near x naught. This is the fundamental approximation of the curve by the tangent line or by the function by this polynomial of degree 1. Let's look at a few basic functions we'll be studying. Let's look at power functions, a variable x to a constant number n. If this is our function, and n is any real number, we will be able to see in this class that the derivative of f is given by n times x to the n minus 1. The way this is usually remembered is you take the exponent and you bring it down, so we have an n here, and then you subtract 1 from the exponent. So bring the exponent down and subtract 1 from the exponent. That's how you take the derivative according to the power rule. Now, we need the ability to prove these things, and we'll eventually prove this, but we'll just do a few cases to start with in the first week. So let's check the case where n is equal to 2 and the function is x squared.
we're going to prove this derivative here using a limit. If f of x equals x squared, then f of x plus h is the quantity x plus h squared. This is nothing subtle here. This is really just typing. We're taking the x and we're replacing it by x plus h. So you just replace x by x plus h. So f of x plus h is x plus h squared. F of 7 is 7 squared. F of a million is a million squared. So f of x plus h is x plus h squared. We look at the difference quotient here, which gives us the average rate of change, f of x plus h minus f of x over h, and we get x plus h squared minus x squared over h. X plus h squared is x squared plus 2xh plus h squared. We subtract the x squared off, and the terms that don't have h in them cancel. That means we're doing the problem right. We're always going to win if the terms that don't have h in them cancel each other. Then this h on the bottom goes into each of the two terms that do have h, and we end up with 2x plus h. So the average rate of change is always 2x plus h, if delta x is h, if the length of the interval is h. Now to find the rate of change, or the slope of the tangent line, we take the limit of the average rate of change, or the slope of the secant line, as h goes to 0. As h goes to 0, what does 2x plus h get closer to? Well, it gets closer to 2x, so the limit equals 2x. Or you can use the limit rules. You can say the limit of a sum is the sum of the limits. The limit of 2x is just 2x, because it doesn't depend on h at all, and the limit of h, as h goes to 0, is not surprisingly 0. So two different ways to end that problem. So now we know the derivative of x squared is 2x, which is what the power rule tells us. Now that we know that the derivative of x squared is 2x, we know the slope of the tangent line to this parabola right here. So let's look at a particular point like x naught comma y naught is 3 comma 9. And let's compute the slope at that point. So the slope is given by f prime of x naught. X naught is 3 here. So 2 times 3 is 6. So the equation of the tangent line here is y minus 9 equals 6 times x minus 3. And that's the equation of the tangent line. The fundamental approximation is that the function itself, which is the y-coordinate of the curve, is very close to the y-coordinate of the tangent line. To get the y-coordinate of the tangent line, you look at the equation of the tangent line, and you add 9 to both sides. So x squared is very close to 9 plus 6 times x minus 3, at least for x near 3. If you'd like to check these things on your calculator, you can pick a number that's near 3. I picked 2.9 right here. 2.9 squared is 8.41. Whereas if you plug 2.9 into the y-coordinate of the tangent line here, you get 9 plus 6 times 2.9 minus 3, you end up with 8.4. And they are close to each other. Okay, great. Let's do another example. Oh, sorry, let's not do another example. Let's look at this graphically. Here's the parabola, y is equal to x squared. Here's the point we were looking at, 3 comma 9. And the tangent line is drawn in green here. And it looks like it has a slope of about 6. If you go over 1, we go up about 6. Right near here, you can hardly tell the difference between the curve and the tangent line. And x squared, the y-coordinate of the curve, is very approximately equal to, it's a good approximation, the y-coordinate of the tangent line, 9 plus 6 times x minus 3. Okay, now we'll do an example. Let's look at the power rule for a negative number. It's true for all real numbers, but let's look at a negative number when n is minus 1. Then we should get a derivative of minus 1 times x to the minus 2, which you can see we do at the very bottom. But let's go through the steps. Let's compute the derivative by taking the limit of an average rate of change. If f of x is 1 over x, f of x plus h is 1 over x plus h. We just replace x by x plus h. And then the difference quotient here, f of x plus h minus f of x over h, is given by 1 over x plus h minus 1 over x over h. We subtract this difference of fractions in the numerator by getting a common denominator. We get x minus the quantity x plus h. So we get x minus x minus h. We just get a minus h on the top. Again, we're happy. The terms that don't have h in them have canceled. We cancel this h. We divide h into h and we get 1. So we have minus 1 over x times the quantity x plus h. If we now take the limit of this expression, f prime of x is the limit of this average rate of change as h goes to 0, we can just plug in h is equal to 0. What does minus 1 over x times x plus h get closer to as h gets closer to 0? Well, it gets closer to minus 1 over x times x plus 0. So the derivative of 1 over x is minus 1 over x squared, which is what the power rule predicts. Let's go ahead and use this information, that the derivative of 1 over x is minus 1 over x squared, to find the slope of a tangent line on this. It's going to be a hyperbola on this hyperbola. So we have the curve y equals 1 over x. Let's look at the point, say, 2 comma 1/2. The slope of the tangent line m is given by f prime of x naught, which is minus 2 to the minus 2, which is minus 1/4. You do the exponent first and you apply the minus sign last. That's just convention for the order of operations. And so the slope of the tangent line is y minus y naught, which is 1/2, equals minus 1/4 times x minus x naught, which is 2. And the fundamental approximation is that 1 over x, which is the y-coordinate of the curve, is approximately equal to 1/2 minus 1/4 times x minus 2, which is the y-coordinate of the tangent line. And this is kind of neat because these two functions don't look anything like each other. 1 over x is a very different function than this polynomial of degree 1 right here. And yet, it's a good approximation. If you pick a number x near 2, I picked 2.05, you get numbers which are at least reasonably close to each other. Let's look at a graph for this one. Here we have the hyperbola, y equals 1 over x. We have a green tangent line through the point 2 comma 1/2. And again, this graph isn't as good actually. My slope really isn't as close to minus 1/4 as it should be. But again, we see the approximation of the curve by the tangent line, and that we can express this geometric fact by saying one function is approximately equal to a much simpler function. That's the fundamental approximation. Okay, so besides power functions, we're going to talk about trigonometry in this class. And we're also going to prove rules. So let's go ahead and not prove the power rule for every real number, but let's go ahead and prove the power rule for positive integers, 1, 2, 3. So we'll do a proof by induction. We'll start with a case with n equals 1. That means the function is a very simple function. F of x is x to the 1, which is just x. So f of b minus f of a is just b minus a, and this difference quotient is always 1. When we take the limit of 1, we get 1. So the derivative of x is 1. That's the base case. Now we're going to proceed by induction on n. We're going to assume we know the power rule for n, and then we're going to prove the power rule is also valid for n plus 1. Okay, so we get to assume this limit right here because that's the power rule for n. The limit as b goes to a of b to the n minus a to the n over b minus a equals what the power rule says it is, equals n times a to the n minus 1. We're going to assume that. And then we're going to show that then it's true for the next number, that if we change n to n plus 1, we get what the power rule says as well. So let's consider the function f of x is x to the n plus 1. Let's assume we know this limit right here because we know the power rule for n. And let's work out the limit of b to the n plus 1 minus a to the n plus 1 over b minus a. You have to learn to do these things. I think maybe you have to read a book or take a class to know what to do at this point. Anyway, you want to insert these two numbers right here in red. Of course, it's always true if you subtract a to the b minus n and then add a times b to the n, and then add a times b to the n. You can always add and subtract the same number. It doesn't change anything. But why would you want to do that? Because if we look at the first two terms, we can factor out a b to the n. We get b to the n times b minus a. And if we look at the last two terms, we can factor out an a. We get a times b to the n minus a to the n. And that's part of the limit that we already know. If we divide these by b minus a, we get b to the n plus a times b to the n minus a to the n over b minus a. This is the limit we already know. So taking limits right here, we get the limit of b to the n, as b goes to a, is a to the n. Oops, that's a typo. I wrote b to the n right here, but it really should be a to the n. The limit of b to the n, as b goes to a, is a to the n, not b to the n, sorry. Plus a times the limit of b to the n minus a to the n over b minus a. But this is the limit that we know. It's equal to n times a to the n minus 1. So this a stays here, and then we get n times a to the n minus 1. So we have a to the n plus n times a to the n is n plus 1 times a to the n. And this shows that if the power rule is true for n, then it's true for n plus 1. And since we checked the case for 1, it's true for 2, and since it's true for 2, it's true for 3, etc. And this is how you prove something for an infinite number of cases. You use mathematical induction. We still have to prove the power rule for negative integers and fractions, and we will later on. Okay, now we'll go to trigonometry. Let's review radian measure a little bit, because in calculus we want to use radians. The formulas of calculus are not true in degrees. The formulas of calculus are only true if you use radian measure. So what is radian measure? Consider an angle POQ, where O is the center of a circle of radius r, and P and Q are on the circumference. Look at the arc length along the circumference from P to Q. And suppose you're walking along this arc, this green arc right here. Count how many radiuses you travel. Maybe if you walk the length of one radius, you get to about here, maybe a little less. If you walk the length of a second radius, maybe you'd go past this point. Maybe this is, 1.7 radiuses or something like that, the way I've drawn it. But anyway, if you take the ratio to the arc length of the circumference S to the radius r, that's radian measure. You've just counted how many radiuses you've walked along the circumference. And that's the definition of radian measure. So for example, if you walk all the way around the circle, you know the circumference of a circle is 2 pi r. You divide by the radius, you get 2 pi. So the radian measure of going all the way around the circle is 2 pi. If you just want to go a right angle, that's just pi over 2. Notice we call radians a unit, but S would be measured in, say, meters, and R would be measured in, say, meters. And so the unit cancels here. So a radian is really a dimensionless unit. A radian is just a number. And here we give the definition of sine and cosine. In pre-calculus, these may have been defined by using right triangles, but in calculus, it's really better to define these in terms of the unit circle. So let's take the unit circle, centered at the origin, x squared plus y squared equals 1. And let's take a ray, OQ, whose radian measure is theta, away from the x-axis. We have a radian measure theta that identifies a unique point here on the unit circle. The x-coordinate of the point Q is cosine theta, and the y-coordinate of the point Q is sine theta. In this way, we have the signs built in. We don't have to change the signs depending on what quadrant it is. We know what the signs are because here, for example, both the x-coordinate and the y-coordinate are negative. Up here where I've drawn Q, the x-coordinate is negative, but the y-coordinate is positive. This also lets us see the fundamental relationship between sine and cosine. Since cosine is the x-coordinate of a point on the unit circle, and sine theta is the y-coordinate of a point on the unit circle, we know that cosine theta squared plus sine theta squared equals 1. And that's the fundamental relationship between sine and cosine. There are other trig functions. There are 4 other trig functions: tangent, cotangent, secant, and cosecant. The cotangent is called the cotangent because it's equal to the tangent of the complementary angle. Remember that angles are called complementary when they add up to a right angle. And in radian measure, a right angle is pi over 2. So the cofunction is the function of the complementary angle. The cotangent is the tangent of the complementary angle. The cosecant is the secant of the complementary angle. And so although there are 6 trig functions, this sort of breaks them down into 2 sets of 3, the function and its cofunction. Right here we see a graph of tangent of x. Notice that it's not defined for all points because when cosine is 0, tangent is not defined. Cosine is 0 for an infinite number of theta, pi over 2, 3 pi over 2, etc. Here are the derivatives of the trig functions. We will work these out in class, but I just list them here. The derivative of sine theta is cosine theta. The derivative of tangent theta is secant squared theta. And I'd like to point out I'm using a new notation here. I'm using this operator d over d theta as take the derivative with respect to theta of tangent theta. If we look at this last bullet, it sort of comments on why we use this notation. If you think y is equal to f of x, and we've already talked about why the rate of change dy over dx should be the derivative f prime of x, then it makes sense to have this operator d blank over d variable. Because dy over dx should be d over dx acting on y. And if y is equal to f of x, we get d over dx acting on f of x should be f prime of x. So we get used to just looking at this symbol here as an operator. D over dx means take the derivative of f of x. And this is a convenient way to express derivatives. We see some nice patterns here. We see that the derivative of the cofunction is the negative of the cofunction of the derivative. So the derivative of sine is cosine, but the derivative of the cofunction, cosine, is the negative of the cofunction sine. The derivative of the tangent is secant squared, and the derivative of cotangent is the negative of cosecant squared. So you only have to remember half the differentiation rules if you want to remember this rule right here. And we'll be able to prove this rule very easily later on using the chain rule. Besides trig functions, we're also going to be using exponential functions and logarithms. Actually, it takes a little bit of work to give a completely rigorous definition of an exponential function. So I won't say too much about that right here, but I'll explain the main point. Exponential functions are some constant base, a, to a variable x. And we know what these are equal to when the exponent is a rational number. Right? A to the 3/5 means take the 5th root of a cubed. So you can plot all the points on an exponential graph for rational numbers, for rational values of x. And you see that this gives an increasing function. And because it's an increasing function, we can use a limiting process to get a continuous curve that represents the exponential function for any exponent x. I'm doing the case where a is greater than 1 here, and in that case, exponential functions increase very quickly. They look like this. They start out very small. When x is 0, they give you 1. When x is 1, they give you a, and then they go up quickly, because each time we increase x by 1, we multiply the y value by a. The logarithm to the base a is the inverse function of a to the x. If we draw on the line y equals x right here, we can reflect our exponential function across this line. I haven't drawn a beautiful reflection here, but the reflection's in red. And that's the graph of the inverse function. So that's the graph of the logarithm base a. The logarithm is not defined for negative numbers or for 0. It comes up when x is 1, it's 0. When x is a, it's 1. And it grows very slowly because the exponential grows very quickly. If you're not used to people making up names for functions, you might wonder what the logarithm base a really means. And the point is here that this sentence here tells you exactly what a logarithm is. A logarithm, to say the logarithm of y base a is x, means exactly the same thing as to say y equals a to the x. These two formulas mean exactly the same thing. That's the nature of an inverse function. Now, these graphs and these values of exponentials and logarithms are maybe not so important as the rules of exponents and the properties of logarithms. It's kind of funny, but the rules that govern these functions are in some sense more important than the functions themselves. So let's review the rules of exponents. The product of two powers to the same base is given by adding the exponents. The quotient of two powers to the same base is given by subtracting the exponents. Therefore, if you let x and y be the same thing, you'll get 1 on the left-hand side, and you'll get a to the 0 on the right-hand side. And so that's some rule we can derive here from the second rule. A to the 0 is always equal to 1. Here, I want a to be positive. I'm really thinking of a as being bigger than 1. And now if you let x be 0, you see that 1 over a to the y is equal to a to the minus y. And this gives meaning to negative exponents. In fact, all kinds of strange exponents are defined to be what they are in order to preserve the rule of exponents. The last rule is if you take the exponent of a to the x, you go a to the x to the y, you multiply the exponents, you get a to the xy. Now if we go back to the definition of inverse functions here, any rule involving an exponential we can turn into the rule for a logarithm. And here are the properties of logarithms. The logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. The logarithm of the reciprocal is the negative of the logarithm. The logarithm of 1 is 0. And the most wonderful property of logarithms, that a logarithm base a of x to the n is n times the logarithm base a of x. Somehow this n can be taken out of the logarithm here. So this is a very useful rule when, for example, you want to solve for an exponent. Here are the derivatives of exponentials and logarithms. The derivative with respect to x of a to the x is a to the x times some constant, times the natural logarithm of a. What is the natural logarithm? The natural logarithm is simply a logarithm to the base e, where e is this number we've talked about before, given by this interesting limit. The natural logarithm of e is 1, so you have simpler formulas when you let the base of the exponential and the base of the logarithm be e. The derivative of e to the x, for example, is just e to the x, because as we said, the natural logarithm of e is just 1. The derivative with respect to x of log base a of x is 1 over x times some number, the reciprocal of the natural log of a. When a is e, we just get 1 over x. So the derivative of the natural log of x is 1 over x. And again, in class, we'll use limits to prove these derivatives. If you know French, you know why the natural logarithm is ln instead of nl. Okay, so we've gone over the functions we're mainly going to be using, the functions from pre-calculus. Let's do a little more motivation, right? Let's get interested in calculus and want to learn all these things and use them. And let's then finally end up by doing some examples of the kind of examples that'll be on the homework. All right, can you summarize calculus? Well, on one slide we can certainly try. Calculus consists of the first half, which is differentiation, and that's what we'll be studying in weeks 1, 2, and 3. Given a function y equals f of x, find its rate of change, dy over dx equals f prime of x. And a second half, integration, where we do the inverse operation. If we're given some rate of change g of x, we try to find the function capital G of x, right? We're given a little g of x. We find a different function, capital G of x, such that the derivative of capital G of x is equal to little g of x. In other words, if you're given a rate of change, can you find the original function? And I see I have a typo right here. This capital G should be a little g. When we learn integration, we'll learn how to do this, how to find the original function given the rate of change. And this will be done in weeks 4 and 5. But you'd think if we really wanted to know what calculus was about, we would ask Isaac Newton. So what does Isaac Newton say calculus is about? The relation of the fluents being given to find the relation of their fluxions and conversely. So the English is already kind of outdated 300 years in the future. A fluent is a variable, something that's flowing with respect to time, or what we would call a function. And a fluxion is what we would call a derivative. So Newton's saying calculus here is about giving a relation among functions, find the relation among their rates of change. We would call this implicit differentiation, and we will cover implicit differentiation in week 3. And now there's an and conversely here, which really implies what? It's the last bullet. Given a relation among the rates of change of functions, find the original functions. We're not really going to do that in this class. There's a separate class called differential equations for that problem. But we will address the simplest case. Given one rate of change, we will find a function that has that rate of change. So that's all good. That's fine. So I sort of understand what calculus is aiming to do, but as a student, what am I actually going to be doing in this class? All right. So as a student, you're going to be doing a lot of homework problems, a lot of practice problems. So let me try to answer that question as well. First of all, we're going to usually pretend that we know a curve. If you remember back to the candy store problem, we didn't really have a curve, we just had a bunch of data points and we drew a curve through them. That's called interpolation. We're not going to worry about interpolation too much. We're always going to pretend that we have some curve that we know. You might see some homework problems and you might wonder, how would somebody know that that's the right curve? We're really just going to pretend that we know what the curves are. And the second thing is we're usually going to pretend that the curve is the graph of some elementary function. What is an elementary function? Well, these are the functions you study in pre-calculus. Elementary functions are combinations, differences, products. You can take compositions, you can plug one elementary function into another. You can find an inverse function of an elementary function. You'll still get an elementary function. So you do these combinations on polynomials, on rational functions. A rational function is a quotient of two polynomials. On trig functions, exponentials, and logarithms. So you combine those in any way you want. Those are the elementary functions. And we're usually going to pretend that whatever function we're dealing with in whatever problem can be given by an elementary function. So here in blue is what we'll spend most of our time doing. We'll find the derivatives, rates of change of functions, usually elementary functions, and we'll find the original functions given rates of change. But these won't always be elementary functions. And we'll interpret these rates of change in applied or word problems. We'll do applications to science to see how these rates of change apply to science. You may say that sounds pretty similar to high school. We'll probably do something a little more on our homework and our quizzes than was done in high school. We will also work with general functions that are not necessarily elementary functions. In college, calculus students need to prove results about general functions. Okay, so we'll be doing some proofs about general functions as well. Okay, so let's go over some examples that might occur on your homework. This first example is from your textbook from section 2.7. The cost of producing X ounces of gold from a new gold mine is costs, capital C, is equal to f of x, is C is equal to f of x dollars. And the first question is, what is the meaning of the derivative f prime of x, and what are its units? So this problem is not asking us to do any computation. This problem is testing to see if we know what the interpretation of the derivative is as a rate of change. So C is the cost of mining X ounces of gold, and X is the number of ounces of gold that you've mined. You can always give the standard textbook answer. You can say the rate of change of cost with respect to X is the rate of change of the cost of production with respect to the ounces produced. And you might even know that economists call that the marginal cost. But it's nice to just, if you want to show you understand something, it's nice to say it with a minimum of jargon, using words that are as plain as possible. So in plainer words, when the mine is producing X ounces of gold, the cost of producing each additional ounce is about f prime of x. Right? That's the rate of change of cost with respect to x. If x goes up by 1, the cost is going to go up by about this rate of change right here, f prime of x. If you want to read the units off, it's better to use this dc over dx notation. The units of cost are dollars, the units of x are ounces, and so the units of the derivative, dc over dx, are dollars over ounce, dollars per ounce. Next question, what does the statement f prime of 800 equals 17 mean? When the mine is producing 800 ounces of gold, right, we're only talking about the time when the mine is producing about 800 ounces of gold. When you're around that level of production, each additional ounce of production will cost an additional $17 approximately. This is the fundamental approximation. This is approximating the curve by its tangent line. The tangent line has a slope of $17 per ounce. So if you increase the number of ounces by 1, your cost will go up by about $17. Okay, there's a third part to this. Do you think that the value of f prime of x will increase, sorry, that's not of, that's or decrease in the short term? You can send me an email with all the typos I've made, and I'll put up a set of slides with those typos gone. Do you think f will increase or decrease in the short term? What about the long term? Explain. Okay, so again, this problem is not asking us to compute anything. It's asking us to explain and show we understand the interpretation of the derivative. So let's just go ahead and do this. It's okay to be long-winded. In the beginning, you have to buy a lot of equipment and hire a lot of people. There's a lot of fixed costs. So the first few ounces of gold you mine are going to be very expensive per ounce. But then as you mine more ounces of gold, that average cost, or that rate of change, is going to go down. Therefore, f prime of x, which is the rate of change of cost with respect to ounces produced, will decrease at first. After a while, the gold that is easy to take out is going to be gone, right? That's human nature. You take the gold that's easy to take out first. And then the gold that's left will be harder to mine, more difficult to reach, take longer to take out, require more expensive equipment, and therefore f prime of x will increase for large values of x. Okay. Here's another problem you might get on your homework. Let y be the natural log of x. First question, what is the average rate? Oh, that's not rate of rate, that's rate of change. What is the average rate of change of y with respect to x over the interval from e to e squared? Well, we know to compute the average rate of change, we do the change in y over the change in x. So that's the function evaluated at e squared minus the function evaluated at e. This function is the natural logarithm. The natural logarithm of e squared is 2. The natural logarithm of e is 1. And so the average rate of change is 1 over e times the quantity e minus 1. Now this is the answer right here. It's approximately equal to this decimal approximation, 0.214. It's always nice to approximate things so you feel like you're doing them right. Question number 2 does not ask for the average rate of change, it asks for the rate of change. So we have to know to use a derivative. What is the rate of change of y with respect to x when x is equal to e? Well, the derivative of the natural logarithm is 1 over x. So when x is equal to e, we plug in e for x, and the rate of change of y with respect to x when x is equal to e is 1 over e, which is about 0.36. Now the rate of change is the same thing as the slope of the tangent line. So the next question, predictably, is find the equation of the tangent line to the curve y equals the natural log of x at the point e comma 1. Well, we really just calculated the slope of this tangent line. The slope m of this tangent line is the rate of change of y with respect to x when x is equal to e. And we just saw that's 1 over e. So if we use the point slope formula for the point where x naught is e and y naught is 1, we see that the equation of the tangent line is y minus 1 equals 1 over e times the quantity x minus e. Now once you know the equation of the tangent line, you can write down the fundamental approximation, and that is the next question here. Use the fundamental approximation to approximate the natural log of x for x near the number e. And then go ahead and compare the approximation with the calculator's value for x is equal to 2.7, and do it to 4 decimal places. Alright, so e is 2.7182, so on and so on. So 2.7 is a number that's close to e. The fundamental approximation is that the natural log of x, which is the y-coordinate of the curve, is approximately equal to the y-coordinate of the tangent line. So we add 1 to both sides. We see the y-coordinate of the tangent line is 1 plus 1 over e times the quantity x minus e. So the natural logarithm, which is a fairly complicated function, has this nice simple approximation for x near the number e. If we go ahead and we put in 2.7 for x, we get that the natural log of 2.7 should be approximately equal to 1 plus 1 over e times 2.7 minus e, which turns out to be 0.9932. I just truncated the digits, I didn't round. If you put the natural log of 2.7 into your calculator, you'll get 0.9932 as well. These numbers are not equal, but the first 4 decimal places agree. All right. So let's just do a summary before we stop. For y is equal to f of x, we learned the interpretation of the derivative. The rate of change of y with respect to x is given by the derivative, which is a limit of average rates of change, or a limit of slopes of secant lines if you want. The rate of change, dy over dx, is the limit of average rates of change. The derivative f prime of x naught has a meaning. It's not only the rate of change, it's also the slope of the tangent line to the curve y equals f of x at the point x naught comma f of x naught. The tangent line is given as a limit of secant lines, and so the slope of the tangent line, which is dy over dx, is given as a limit of slopes of secant lines, as a limit of delta y's over delta x's. Once we know the slope of the tangent line, we can write down the equation of the tangent line to the curve. It's given by the point slope formula. And once we have the equation of the tangent line, we can write down the fundamental approximation for any function that has a derivative. Now, not all functions have derivatives, but elementary functions have derivatives at almost all points. We see that f of x is approximately equal to f of x naught plus the rate of change, f prime of x naught, times the change in x minus x naught, at least for x near x naught. And this is the basic approximation we'll use throughout this class. And the last slide right here is always a thank you slide to let everybody know that we're done. Right, so thank you for listening to this, and I look forward to any questions you have in class. Thank you.